Okay, Giancoli 4A. We're just going to talk about friction. So when we look at things rubbing, or surfaces rubbing against each other, right? We know that if something's dragging, there's going to be some kind of contact between these two surfaces. This contact between surfaces, when an object's going across it, is called friction. Um, there's two types of friction, kinetic and static. We're going to call this kinetic. If an object is moving across the surface, it's kinetic friction. So the force of friction is equal to the coefficient of kinetic friction, which is just our number, and we'll get to that, multiplied by the normal force. This coefficient, and you can see here, it's different for every pair of surfaces. So as you can see, we have our kinetic friction, and you can see if we have two surfaces that are wood and they're rubbing together, that's the coefficient of kinetic friction. But you can see that the numbers will vary based on the different surfaces. Now we're talking about static friction. Static friction is different than kinetic. Static friction is the friction you have to overcome to get an object to move. So if we have two objects that are wood and we're trying to get one to start moving or slide across it, it's going to take a little bit more effort. So therefore the coefficient of friction is higher. And you'll always find the static friction coefficient higher than that of the kinetic, unless it's something that's really, really friction free, as you can see in the bottom ones. But kinetic as we're moved, static to get it to start moving. Static friction, I just said that, is the frictional force between two surfaces that are not moving along each other. This is what keeps something going. So it's what keeps an object on an incline from sliding, objects from moving when a force is first applied, etc. And so the force of friction, right, the static friction times normal force is gonna have to be greater than or equal to the force of friction in this case. Now, when we look at static friction, so let's say we have an object and we're trying to get it to move. We're going to apply a force, not moving, not moving, not moving, not moving, not moving, not moving. And then once we reach this point where our applied force is equal to friction, the object will start moving. Chances are it'll move at a constant velocity, and then it will speed up as we start to get it moving. And then if we can keep our kinetic friction equal to our applied force, then we can go to constant velocity. But you can see, this is to get it to move. Once we start moving, then we go to kinetic. If we have inclines and friction and incline problems, I have another video on that, and you'll be watching that also. But you have to account for normal force, gravity, and frictional force. And here's the key to incline. Normal force is always perpendicular to the surface. Gravity is always down. And then friction is always parallel, okay? And if you can remember that, then you're fine. So if an object is sliding down, friction goes up. If you're pushing an object up a slope, then friction goes down. But it's always going to run parallel to the surface. If an object is at rest, the forces are the same. With the static frictional force, and the sum of the forces is zero. And we'll see some examples of that. So here's friction, static versus kinetic. We have a mystery box on a floor. We have our coefficients. We want to determine the frictional force acting on the box if a horizontal force is applied to it of different magnitudes. Do it now. Okay, so example 416 is a good one. Static and kinetic friction. So we have a box, 10 kilograms of mass. It's sitting on a horizontal floor. We're going to apply a force, different forces, to push it. Friction's pushing back. My free-body diagram will have gravity always there, and since it's on a flat surface, normal force is going to be perpendicular to that. And it's going to accelerate in the horizontal, okay, not the vertical. So first step is to find the force of gravity, which is mass times 9.8. So 98 newtons. If my weight's 98 newtons, and I'm not accelerating in the vertical, my normal force is also 98 newtons. Little trick there, you don't have to do a whole lot of math that way. Now, to find the force of friction is just normal force times the coefficient of friction. Now, there's two new coefficients of friction here, static and kinetic. Static is you're pushing, just get it moving. So this is what you'll have to overcome to get it to start moving. Once you're pushing on the ground, it's always easier because friction's less. And usually the coefficient of kinetic friction is after you already have it moving, okay? So we want to find the force of friction at different times here. So let's say we're applying zero force. Okay, so our force applied zero. These forces are balanced, so we're only worried about here. So net force is MA, right? Force applied minus the force of friction equals the mass times my acceleration. If we push with a force of 0, right? That means we're going to have a force of friction equal to 10 times my acceleration. Since we're going to just push it, right, to get it going, our acceleration is essentially going to be 0. So 0 minus force of friction equals 0. So our force of friction is obviously going to be 0 because we're not applying any force, so it's not going to move. So our answer to A is 0. B, same idea, except B, our force applied actually has a number. So force applied is going to be 10 minus our force of friction. Our static's 0.8, so if I take my normal force of 98 and I multiply it by 0.4, that's how much it's going to, how much friction there is. So 98 times 0.4 gives me 39.2. So if I see this, and again, I'm just getting it started, so my acceleration is essentially going to be 0. 10 minus this gives me a negative answer for my net force. And if I'm applying a force this way of only 10 newtons, I cannot overcome friction. So that means this object is not going to have any acceleration, right? The frictional force is still 39.2, but in this case it's going to be 0 because I'm not moving it. To have frictional force, things have to rub. So now let's look at C. We got C, my applied force is now 20 newtons. Minus 39.2 equals 0. As you can see, I'm not moving this thing, so it's still 0. And you can also see D, since it's 38, right? It's still less than 39.2. Therefore, I am not putting enough force on it to make it to move, so D is 0. So letter E states 40 newtons. So my net force is this minus this, so 40 minus 39.2 equals 10A. Now I'm going to have a little bit of acceleration here because I'm going to have a net force that's going to be greater, or the applied force is going to be greater than friction. But it's only 0.8. So if I divide both sides by 10, this acceleration is going to be minimal. 0.8 divided by 10, and I'm going to barely accelerate it. Just to get it started. And again, the reason we use static friction is we're applying the force just to get it to start moving. And then we can see what the acceleration is there. Box against the wall. You can hold a box against a rough wall and prevent it from slipping down by pressing hard horizontally. How does the application of the horizontal force keep an object from moving vertically? Do it now. All right, so box against the wall. We're holding a box against a rough wall, and we're preventing it from slipping down by pressing hard horizontally. So we're pressing the box against the wall. It'd be something like this, right? I'm holding this box against the wall like this. And it says, how does the application of the horizontal force keep an object from moving vertically? Well, vertically, if I take that force away, which I guess I could show you, if I take that force away, gravity's going to win, okay? And two things. As I apply force and the object's not moving, whatever my force applied is going to be equal to the normal force because it's not moving in the horizontal at all, right? So knowing that, and I know when I have a normal force times my coefficient of friction is going to be my frictional force. And if I'm holding it in place, frictional force is equal to gravity. So by putting an applied force, I'm giving it a normal force, which then gives it a force of friction, which then opposes gravity wanting to pull down on it. Okay? So when we're pushing something against the wall, this is what a free body diagram should look like. But as soon as I remove this, I remove this, if I remove this and I remove this, which leaves me just with gravity, box drops. Pulling against friction, a 10 kilogram box is pulled along a horizontal surface by a force of 40 newtons applied at a 30-degree angle. But now there's friction, and the coefficient of kinetic friction is 0.3. Calculate the acceleration. Do it now. All right, so we're pulling this box at an angle, 30-degree angle with 40 newtons of force. It's a 10 kilogram box, and we're dragging it along. First thing I want to do when I see an angle is I want to take my force vector of 40 newtons at 30 degrees, and I want to break it apart into x and y of my force applied, all right? So my force applied, I'm going to break apart into two separate entities here, and that's just trig. So I have my hypotenuse is 40, and my angle's 30. So my x component is going to be 40 cosine 30, and my y component going up is going to be 40 sine of 30. So this is 40 sine of 30, and this is 40 cosine of 30. All right, and so now I can use this to find my weight, or the force of gravity, 10 times 9.8, which we've already established is 98 newtons. Now, my normal force isn't going to be 98. All right, here's what we want to think about. We want to think about our forces in the y. I have normal force plus the y component of my applied force, which is 40 cosine 30. So 40 sine 30, and I get 20. So I have normal force plus 20 will equal my y component, which is 98. I subtract 20. My normal force is going to be 78. So normal force is 78 newtons. And then my applied force from the tugging of the cord is going to be 20. That helps me find friction. Friction is normal force times coefficient. So 78 times 0.3. So my force of friction is 23.4 newtons. And then my applied force in the horizontal, 40 cosine of 30, is 34.6 newtons. Okay, so I'm tugging with this much force of friction. Now to find the acceleration, sum of my forces is ma. We're just talking about the horizontal. I take 34.6, my applied force, minus my frictional force of 23.4, and that should equal my mass times my acceleration, which is 11.2 equals 10a. Divide both sides by 10. My acceleration is 1.12 meters per second squared. So first step when you're pulling at an angle, break it up into x and y components so you see the horizontal and vertical. Remember, these two together add up to our weight. So normal force isn't going to be equal to weight when we're pulling at an angle. So keep that in mind. And then also then you just use the unbalanced forces then to find your acceleration. To push or pull a sled. So your little sister wants to ride on her sled. If you were on flat ground, will you exert less force if you push her or pull her? And there isn't a right answer here. Now we're assuming the same angle. So here we are. We're pushing, right? And the angle's going down. And here we are pulling at the same angle, but now we're pulling up, okay? So let's look here. So if we're pushing down, when we push down, we're actually adding to the gravity because we're pushing down plus gravity. So our normal force is going to be higher when we're pushing down. When we're pulling up, we're applying a force upward, and the upward applied force plus normal force equals our weight, which means our normal force is going to be less than our weight. Here, our normal force is going to be more than our weight. So if we're talking about which one's going to be easier, definitely pulling, because that way our normal force will be less than our weight, which means friction will be less. And then two boxes in a pulley. We have two boxes, one 5 kilograms, one 2 kilograms, and we're going to let them go. We know the coefficient of kinetic friction is 0.2. And we're ignoring the mass of the cord and the pulley system, and we're going to find the acceleration of the system. A and B will both accelerate the same since they are attached and the cord doesn't stretch. Do it now. Okay, two-body problem with a pulley, and we have friction involved now. So I mean, frictionless surface is obviously easier because it's easier to see forces. But the first thing we want to do is we want to draw free body diagrams for each. So this was box A, I think, and this was box B. So for box A, here's what we got. We got tension force from that string. We got normal force from the ground pushing up, or the table pushing up, and then we have gravity, which always exists, and then we have our frictional force going off to the side. A lot of stuff acting up here. Box B looks like so. Box B has the force of gravity, and it has the force of tension going up. So we know what's going to happen, hopefully, right? We expect this thing to go down if we got enough force pulling down on it. Guess we'll see if it's enough, right? The assumptions we make in this is that the cord has no mass, and also that the cord doesn't stretch it. So it's a solid cable, and it just pulls and rolls along the pulley. We're going to assume that the friction of the pulley is going to be included with the friction rubbing on the surface of the table, so we don't have to think about two different types of friction going on here. But I think we're good, so now let's think about equations for this one. And we're going to this one's going to accelerate here. This one's going to accelerate here, right? So when we talk about box A, m times g, 5 times 9.8, can't do that one in my head. 5 times 9.8, well, I should have been able to, right? 49 newtons, which means my normal force is 49 newtons. Force of friction is normal force times coefficient, so 49 times 0.2. Force of friction is 9.8 newtons. So now I've got a lot of numbers here. Okay, the only thing I don't know is the force of tension. But it'll be the same for both, because tension's the same throughout the rope. So let's write an equation here. Nothing in the y, we're worried about the x. So I'm going to say box A, net force equals ma. I'm going to have this one going this way, so I'm going to say plus, my friction is going to be minus 9.8, equals the mass of my box 5 times its acceleration. So that's going to be my equation for box A for acceleration. For box B, again, net force equals ma. I got gravity in here. Box B is 2 kilograms. So that's mg. M is 2, G is 9.8. 19.6 newtons is the force of gravity on box B. So then my net force is going to be, this is negative, that's positive. If you want to do that, that's fine. My force of tension minus 19.6 equals 2a. So I have two equations, two unknowns. This is all going to be algebra from here. I'm going to do substitution method. I'm going to bring this over, so 2a plus 19.6, and I'm going to substitute it into here. So I'm going to bring this down here, and I'm going to say 2a plus 19.6 minus 9.8 equals 5a. Okay, so I subtract 2a. It's 3a. 19.6 minus 9.8 is 9.8. And I divide by 3. And 9.8 divided by 3. 3.3 will be my acceleration. So this is going to be 3.3 accelerating. And that means that this will pull down. If I wanted to find a force of tension, I would take that, substitute it into here, and I could find my force of tension pretty fast. If if I needed to. But just understand here, my acceleration would be a negative number, right? So I'd probably put it in here. I would put acceleration in here and solve for force tension just to keep things positive.